Let's look at an example and see if we can get a better feel for how to use those equations for our general case. So in this example, we just want to write the node voltage equations that we could use to find a transfer function which is equal to V sub C of S divided by I of S. But notice in our circuit here, we're given our circuit in the time domain. So right now we're in the time domain, and our first step should always be to transfer this to our frequency domain, unless of course we're already given the circuit in the frequency domain. And as we saw, the reason for that is because it makes our life a lot easier if we start with component impedances as opposed to getting equations in time and then from there doing Laplace transform to go to frequency. So to convert this circuit to the frequency domain, remember our resistors, essentially we're just changing each element to its impedance. So our resistors just stay the resistance value, so that has an impedance of R2, this has an impedance of R1. Our current source is now I of S. Our inductor impedance, remember, is S times L, so this is L1, and this is S times L2, and our capacitor impedance is 1 over SC. So 1 over SC. And of course we're interested in our capacitor voltage, which is now V sub C of S. So now we've transferred our circuit to our frequency domain. So now we're ready to write our node voltage equation. So I'm kind of going to scroll back and forth between our equations. It might be helpful if you just have these up in front of you as well. That might work a little better. So first of all, we can say, well, how many of these equations are we going to need? So in order to answer that, we need to define how many essential nodes we have in the circuit, our N sub E. So remember, an essential node is anywhere we have 3 or more elements connected. So we can see we have an essential node here, an essential node here, and an essential node all along the bottom. So in that case, we know that we have N sub E equals to 3, and from up here, and I don't know that I wrote this explicitly, but we can see that we're going to need N sub E minus 1 equations. So in this case, N sub E minus 1 is 3 minus 1, which means we're going to need 2 equations. So essentially, for this problem, we're just focusing on the first 2 equations. We don't need anything beyond that. If we had another essential node, we would need a 3rd equation. So you can kind of see how that would scale up. Okay, so let's go ahead and label these, and let me move this, or actually let's come down here to our frequency domain. So this is where we're going to be applying this node voltage. So let's call this bottom one our reference node. And again, we're not worried about sort of the underlying analysis why we do that. If you're interested, I'm happy to give you some more pointers on that, but for this class, we don't really need to know too many details about node voltage method. So let's call this one up here in the top left our node 1. Top right, let's call this our node 2. So then by definition, this will be our node voltage V1, and this will be our node voltage V2. All right, so now we need to write our node voltage equations. So if you're a double E, and we've done this before, you can use whatever techniques you're comfortable with, but maybe you're a little out of practice, or maybe you're an ME who hasn't seen this for a while. What you can do is just come back to this general equation. So for our first equation, again, we want to take sum of admittances connected to node 1 and multiply all of that by V1. So let's come down here and apply that. So this is going to be our equation for node 1, or you can label it equation 1. It's usually a good idea to label it just to keep track of what you're doing. So now all of our admittances connected to node 1. So connected to node 1, we have this resistor, this inductor, and this resistor. So all 3 of those touch node 1, so we're going to include all 3 of those. But remember, we're talking about admittances, which is Y is equal to 1 over the impedance. So that means I'm going to put 1 over R1 plus 1 over S times L1 plus 1 divided by R2. And then we multiply all of that by V1. And I'm not going to include the of S again because sometimes it can be confusing. It looks like you're multiplying by another S. That's up to you. If you prefer to leave it, that's fine. Just be careful not to confuse yourself. Okay, so moving on to our next term then. So our next term, we see we have sum of admittances common to node 1 and node 2. We're subtracting, and we're multiplying that by V2. So coming back to our circuit, we're now looking at things that are common to node 1 and node 2, And so of course we can see we have this R2, which is touching both node 1 and node 2. So what we want to do then is we come in here and we're subtracting this term, remember, and we are doing admittances, so it's 1 over R2. That's multiplied by V2. Again, I'm going to exclude the parentheses S. We know it's a function of S, so I'm not going to write it so I don't confuse myself with extra S's. And so now we don't have a third node voltage, so we don't have any more terms here because we only have V1 and V2. If we had V3, we'd have another term there. And now on the right side of the equation, we need sum of applied currents at node 1. So again, we come down here, we're looking at node 1, and we see we have this one applied current source here. So what we're going to do is set this equal to I of S. And again, to be consistent, let me just leave off that S. Okay, so to be consistent with my notes, I'm going to call this equation A. All right, so that was node 1. So now let's look at our node 2 equation. And so we're basically going to follow that same procedure. So let me just scroll up here. So now we're looking at this second line. And so of course we can see our first term here is admittances common to 2 and 1. Again, this is a negative term times V1. So let's come back here, and of course we already said we have R2, which is common to node 2 and node 1, so we have minus the admittance of that, which is 1 over R2, times V1. Our next term is going to be adding, so we're adding sum of admittances connected to node 2 times V2. So coming back to our circuit, connected to node 2, we have R2, we have this capacitor, and we have this inductor. So we're going to need the admittance of each of those three items. So again, we're adding. So the admittance of that resistor R2 is just 1 over R2. The admittance of the capacitor is 1 over SC. So I'm just going to write that as SC. And then for our inductance, the admittance is 1 over SL2. All of that multiplied by V2. And again, we're not going to have a V3 term because we don't have a node voltage V3 and nothing beyond that. So now we're looking for sum of applied currents at node 2. So these are currents that are directly applied to node 2. We see we do not have any currents connected anywhere to node 2, so we're just going to put a 0 here. Okay, and to be consistent with my notes, I'm going to label this as equation B. Okay, so those would be the two node equations we would need. So notice the question just asks us to find the node voltage equations that we could use if we wanted to ultimately find that transfer function. So let's sort of not solve it completely, but let's take this a step further and say, well, let's find that transfer function. Well, there's a few different ways that we could do this. Probably the best and easiest way is to use something called the matrix method. And so if you're a little fuzzy on what that is, I'll be happy to help review, just let me know. But of course we have a lot of variables in here. Even if we knew values for our resistors, our inductors, and our capacitor, the problem is we would still have these S terms. And so because we have these S terms, we can't necessarily use our matrix method the same way we have with time domain circuits where we just had constants floating around. So sort of the most efficient way to do that is to use some type of software, particularly MATLAB. And so in a video later on, or most likely in class, or maybe both, we'll go over how to solve this problem specifically, as well as sort of the more general procedure using MATLAB. You can still do this by hand. It's a little more tedious, but you can do it using something called Cramer's rule. And again, it's a fairly straightforward concept. We'll look at it in a later example with mechanical systems, but the math just gets really tedious. Now for this system, because there's only two equations, we can do something a little simpler, and that is just simple substitution. So how could we use substitution? Well, what we could do if we wanted is we could take our equation B and we could solve that for V1. So we could say solve our equation B for V1, and so that's of course sort of an attractive option because that's multiplied by a relatively simple term. And then we take that V1 term and substitute into our equation A. And from there, we could solve that equation. So then that equation A is only going to have V2, so we would have gotten rid of this V1 term. It'd be something in terms of V2. So then we can take that and we could solve for our transfer function, which again was V2 over I. Well, not again, but I can say that's V2 over I because coming back to our circuit, we see that V2 and V2 and VC are defined between the same two nodes, so we can say V2 equals VC. So hopefully the main takeaway I want you to get here is hopefully you're a little more comfortable using those general equations to get node voltage equations similar to this. Don't worry yet about solving these equations. We'll come back to that in another video.